Okay, practice problems. Yoo-hoo! All right. So we're going to start off with this problem. Here's our system. 2 inputs, 2 outputs. Here's our transfer function. In this case, it's nice diagonal form. This is obviously a contrived example. So here's this diagonal form. So one of the nice things about a diagonal form is that makes computing the singular values for it really simple because they're associated with the magnitude of the diagonal values. Okay, so if I can go through and I can do sigma for a system that has these, and this is the plot that I would get. This plots all the singular values. Okay, so notice that the singular values change in terms of which one is the largest one. So for example, here the first singular value comes out to be this, the second, and notice that at some point what was the largest becomes the smaller, and what was the smaller becomes the larger. So you can have that kind of thing happening. So the H infinity norm for a system is associated with the largest singular value over all frequencies. So in this case, which is the largest singular value? Boom. Well, we bring gamma in and we find that in fact there's more than one place where we have singular value. So that kind of thing can happen too. There can be more than one frequency at which you have the exact same value. And so, but either way, gamma is the largest of the singular values over all frequencies. So this is one way to compute the H infinity norm. And notice by doing a sigma plot, we can actually get a good estimate of the H infinity norm, even if we don't get the exact value. Okay, so I can see that there's a peak here. That's roughly the maximum. There's a peak here. I can check the actual values. I can zoom in and find what those values are, and I can get pretty close estimates, even without actually going through. But notice that what we've actually done is we've actually plotted a lot of values, okay, in order to be able to see those maximums. So there's actually a lot of computation that actually has gone on just to get this plot. All right, another way of computing the H infinity norm involved the bisection algorithm. The bisection algorithm had 2 parts. The first part was the doubling algorithm. So for that system, I basically started with 2 times the magnitude at 0. So notice the maximum magnitude at 0 was this value, which is minus 10 dB anyway. And so we started off with those values. So that is our initial value. So notice that our initial lower bound was 0. Our initial upper bound was twice the magnitude at the origin. So this green line here actually shows what the actual H infinity norm is. So we don't know that. We don't know that yet. I'm just plotting it so you can see what's happening. So we plugged this value of gamma in to our Hamiltonian matrix. We check the eigenvalues to see if the eigenvalues are on the imaginary axis. In this case, they are going to be on the imaginary axis. And so that shows that this is a lower bound. So we double it. So we start here, we double it, we get this value. This value now, which is not an upper bound, must be a lower bound, and so we move up the lower bound to this point. So now we have this region of uncertainty. Okay, so we have this region of uncertainty. We go through and plug this value of gamma into our Hamiltonian matrix. We check the eigenvalues. Because this value is below the actual H infinity norm, we know that this is still not an upper bound, so we double it. Okay, and this becomes our new lower bound, and our upper bound is there. Okay, now when we check this value, we see that if we plug that into our Hamiltonian matrix and check the eigenvalues, that I do not get eigenvalues on the imaginary axis. So this is truly an upper bound. So the doubling algorithm keeps doubling this value until we get a value that is truly above the H infinity norm. And you can tell it's above because when I plug that into my Hamiltonian matrix, I don't get imaginary axis eigenvalues on the imaginary axis. So this then concludes our doubling algorithm. And so we now start the bisection algorithm. So the bisection algorithm starts with an upper bound and a lower bound. And we start with the initial guess of our infinity norms halfway between the two. In this case, it's actually pretty close. But it is below. Well, so we progress through our bisection algorithm. So at this value of gamma now, I can see, if I plug that in, I'm going to get imaginary axis eigenvalues. That tells me that that is a lower bound. So this lower bound moves up to that point. The upper bound is still an upper bound. We just leave it there. We don't have any way of updating that. And so now here's my new lower bound. Here's my upper bound. I take halfway between the two and I check to see if the Hamiltonian has purely imaginary eigenvalues. In this case, it will not. That tells me this is an upper bound. And so I move my upper bound down. The lower bound remains the same. Again, choose halfway between the two, check, and I find that it's above. And so this value becomes the new upper bound. The lower bound stays the same. I take halfway between the two. It turns out this value is actually a little bit below. That means that is the new lower bound. The upper bound stays the same. And I just keep going until the upper bound and the lower bound are really, really close to one another. And so basically what this shows is how many steps it takes for the algorithm to converge. So at this point, the algorithm converges. That is, the upper and lower bounds are so close to each other that we have a fairly good confidence of what the actual H infinity norm is. So that's an illustration of what the bisection algorithm looks like. So at each step, we're having to plug in a new value of gamma, check the eigenvalues of the Hamiltonian matrix to see if they're on the imaginary axis, and so forth. Incidentally, the same bisection algorithm works for discrete time, but instead of the Hamiltonian matrix, you use the symplectic matrix, and instead of checking to see if they're on the imaginary axis, you check to see if they have magnitude equal to 1. That is, if they're on the unit circle. Okay, so we have those two differences, but the algorithm is basically the same. You keep adjusting the upper and lower bounds until you get them right on top of each other. For our next example, we start off with this system. Again, there's a 0D matrix, and we can compute the transfer function for this system. We can obtain the Bode plot for this system and find that the maximum is, we can actually find the maximum. In this case, it happens to be this quantity. Okay, so we can do that by doing a doing the Bode plot and zooming in. So 3.46, it's above 3.4, below 3.5. So let's look at the Hamiltonian matrix when we use 3.5, which is above. So we plug it in. So here's our Hamiltonian matrix. We plug in our ABC matrices and gamma, and this is the matrix that we get. Check the eigenvalues for this, and these are the eigenvalues. Okay, so notice that these eigenvalues, there are 4 of them. So remember, this is a 4th order 4x4 matrix. There are 4 eigenvalues. So remember, it's symmetric with respect to the real and imaginary axis. That's why we have plus and minus real part, plus and minus imaginary part. So we have all 4 combinations. Okay, and I can see that the real part is not 0. Okay, so that means this gamma is an upper bound. Okay, now when I go to 3.4, this becomes my matrix. I check the eigenvalues, and I notice that in fact these are purely imaginary eigenvalues. And so that's what we get. So when gamma is 3.5, we did not get any purely imaginary eigenvalues. When gamma is 3.4, we do get purely imaginary eigenvalues. Now what happens when gamma is equal to 2 root 3, which is the actual H infinity norm value? I plug that in. This is my Hamiltonian matrix value, and I can check that I get repeated eigenvalues on the imaginary axis. Okay, they are on the imaginary axis and they're repeated. Okay, so you can actually show that this is actually the H infinity norm, because if I just go infinitesimally greater than this, my eigenvalues will not be imaginary. They will not be purely imaginary. Okay, so this is, in a sense, the limit as I drop down gamma, and I get an exact value in this case. So in this case, the eigenvalues are on the imaginary axis and they're repeated. So that's what happens in this case. So we've computed the H infinity norm. What about some of the other norms? Well, in order to use the other norms, I compute these controllability Gramians, observability Gramians. Notice that for this Gramian, for this Lyapunov equation, instead of having a Q here, we have this matrix C transpose C, which is kind of different. But the fact that here it involves C and A and C, that gives us something called observability. Here, this involves A and B, that gives us something called controllability. We're going to come back later in the next unit and look at controllability and observability. So I have these solutions to these Lyapunov equations. So recall that the H2 norm is related to those solutions. So in the H2 norm, we have the trace of C times Q times C transpose. Now in this case, when we multiply this out, we get a scalar, and so it's its own trace. So ordinarily you would stick the trace in here, but in this case, the result is a scalar, so we don't need a trace. And so I get this value 9 halves. If I use this form, again, with the trace, so again, this is a scalar quantity anyway, so we still get the same value, 9 halves. So regardless of which form we use, we get the same result. So if I now, so that's H2 squared. If I take the square root, I get this expression, 3 over root 2, which is this value. So we get an exact expression for the H infinity norm, actually, and the H2 norm. For the Hankel norm, we would calculate the largest eigenvalue of this product, P times Q. So we multiply P times Q. This is what we get. We look for the eigenvalues. So here are the eigenvalues. And so the H norm, so I have plus and minus. I use the plus version. And so that's the norm squared. I take the square root and I get this expression. So 2.427. Finally, I go through and I compute the H norm, the one norm. So here's H of t, the impulse response. This is what I get for the impulse response. I go through and compute this integral, which is kind of complicated because, again, this, as a sinusoid, it goes positive and negative, positive and negative. So you actually need to go through and take the absolute value of everything, which makes the integral a lot more complicated. But I did it. Woohoo! And here it is. It's kind of a complicated expression. And so this is the expression I get. And when I actually multiply it all out, this is the value I get. And so that's the one norm. And so we saw this relationship, H2, H, infinity, and 1. And we can see the values here. For this example, I can see that truly H2 norm is less than or equal to the H norm, the Hankel norm, less than or equal to the infinity norm, less than or equal to the 1 norm. So I actually have that here. Now, MATLAB can do a couple of these. So MATLAB has the function norm that will compute the 2 norm and the infinity norm. Okay, so for the system, I can type in this code, do the 2 norm and the infinity norm, and I get the exact, I get numerical values for these two. Now, we also saw that it wasn't that complicated to compute the Hankel norm. All we needed to do is take is to compute the 2 Gramians, the 2 Lyapunov solutions, and compute it this way. It doesn't require an iterative approach. I can do it directly this way. So that wouldn't be too bad to calculate, but there isn't a standard formula for that. That's not one of the norm options for systems. So for an LTI system, the MATLAB actually has implemented those norm calculations into this. So in particular, I can compute the H infinity norm. I don't actually have to plug things into the Hamiltonian matrix, and it does whatever it needs to do. I don't even know what algorithm specifically it uses to calculate the H infinity norm. So I've shown you using the Hamiltonian matrix or the symplectic matrix But you can also do it using linear matrix inequalities. That would be another way, and there are efficient tools for doing that. So I'm not sure exactly how it solves it, but it gives you the value. So these are practice problems.